It's my pleasure to bring you to the final session of the workshop. Well, I say the final session, but we have a discussion session planned for after this, and I hope that that will be an opportunity to do something different and to make it really worthwhile participating. So I hope you'll stay for that. Our session today, the final session, is three fantastic speakers, and what is exciting for me is how these three speakers span the interdisciplinary, multidisciplinary nature of what this workshop is about. So our first speaker, Hsin Chen, has a prize for his PhD in computer architecture. This doesn't look like a computer architecture venue, but I think he's going to tell us that it kind of should be understood as such. We have later on Walterio and later on Boris covering different aspects of this subject area. So Hsin is currently a research scientist at Facebook, working in augmented and virtual reality. He's most famous for his thesis work on Iris, which I imagine will feature a little bit in your presentation. Please, may I invite you to share your screen and tell us what you'd like us to hear.
All right. Let me start the presentation. So hopefully everyone can see the slides.
Yes, looks good.
Okay, awesome. So thanks again for the introduction, and good afternoon for our friends from Europe, but also good morning and good evening for everyone around the world. It's really a pleasure to present in this workshop. From the talks today, we can see that there are many interesting topics about different sensing and compute techniques to enable vision processing near the sensor. So in this talk, I'd like to approach it from a application and system angle to talk about where we are building at Facebook Reality Lab and why I believe there are many exciting research opportunities in this area. So specifically, I'll dive into our efforts on co-designing the hardware and software stack for AI to enable augmented reality, or AR. So first, let me give some quick introduction on our vision for AR and what it can do for us. Consider this glass that we are wearing. It helps us to enhance our vision. But what if it can also enhance our perception of the world as well? So today, we rely a lot on laptops and smartphones to get information and stay connected with each other. But we believe in the very near future, AR devices such as glasses are going to replace them and provide a lot more value. The glasses can offer virtual reality, augmented reality, and everything in between, so that we can take advantage of mixing virtual and real worlds according to our needs. We will be able to wear them all day and interact with it in several very intuitive ways, such as using our voice and gesture, so that it can benefit many different aspects of our lives. So let me give you some examples. So imagine you're walking in the dark outside, and it's very hard to see clearly. What if you can brighten up the scene you see with just a gesture, and it will look very natural without being very noisy? And imagine you're away from your loved ones that you want to spend time with, which is especially true for many people in the past year due to the pandemic. What if you can spend time with them virtually anywhere in the world in a way that it feels just like they're right next to you? Also, imagine that the glasses not only can give you 20/20 vision, but way beyond that, so that you can see like a superhuman. With AR, these are all possibilities. But we don't have to stop there. We can also build a glass to help improve our memory and cognition. Imagine you are in a business meeting and the device can automatically show relevant data based on the context of your discussion. Or if you're traveling, you can have the translation seamlessly right in front of your eyes to help you explore more places. Or when you're doing some grocery shopping, the glasses can send you reminders and directions based on your habit. But we don't want this technology to be dumb. We don't want the glasses to just show notifications all the time. It can be very annoying while you're driving or just chatting with friends. What we really need is for AR to be context aware. And what it would take is always on context aware AI to make that happen. To this end, you can think of AR as a personalized assistant with a perfect memory to answer your questions or requests when you need it. This is our vision of what AR will look like. And what does it take to get us there? First, we need really high resolution displays to overlay high fidelity virtual information. We also need eye tracking to help recognize what we're focusing on, which also requires the capability to do image recognition and semantic segmentation. There are also a whole lot more technology that needs to happen. For example, we need world locking and depth sensing to attach virtual information to a real world objects, even if you or the objects are moving. So all of this is to say that even for a very simple use case, it requires a lot of technology to come together at once. Many of them do not exist, and many of them exist in a different form factor that can be very challenging to port onto a device like a pair of AR glasses. So to deliver the best user experience, really need to deeply understand the user context. And that is a very interesting research area requiring efforts all the way from algorithms to the sensor designs. So if we look at the characteristics we'd like to see in AR glasses, it has to be socially acceptable. Basically, it has to look like the glasses you and I are wearing right now. Also, it has to be lightweight, so we can wear it all day without discomfort. At the same time, it also has to have the battery life to last for an entire day, so we don't have to charge it during the day, which could be a deal breaker for many people. Also, because it is a device that sits so closely to your face, you really have to be really careful about constraining its thermal dissipation, so it won't cause any discomfort. In terms of technology, these are the ones we've talked about already, and we need all of them to come together. But there's one component that stands out. Basically, AI is going to play a very critical role for all of the other components. It's already pretty common for us to use AI to enable computer vision or speech processing. But it is also very important for things like the physical design of the glasses. For example, we can use AI to compensate the quality and the quantity of the sensors on the glasses, which can eventually help us make the glasses lighter and even more efficient. Now, we not only have to enable AI on AR glasses, we also have to run those models locally on the device. And there are several reasons why we need to do that. The first and foremost is privacy, because these glasses are constantly collecting data and looking the world as the way we're seeing it. So we really need to make sure that the data it collects only stay on the device instead of being shared externally without your consent. The second is latency, because we want the device to react very quickly, especially in many AR applications, even a few milliseconds matter. The third one is connectivity. Sometimes you might be in places where you don't have internet connection, and you would still like the AR glasses to work for functionalities that only require the information around you. And the last but not least is energy. This may sound surprising to many people, but processing data locally in many cases can save a lot more energy than sending data to process in the cloud. This is because wireless connection is not cheap, and sending raw data itself sometimes can be too expensive. So those are the reasons why we're investing a lot in making sure we can do the majority of the AI processing needed on the device itself. But AR applications are not homogeneous. They come in different shapes and sizes. I'm going to show you a list of example AR applications that have very different requirements. And we are going to focus on the 4 different axes here, including memory bandwidth, latency sensitivity, and how frequently we expect to run those applications and their compute intensity. As I go through the list of applications like speech processing, video understanding, eye and hand tracking, and many others, you can see that they all have very different requirements. Some of them, like video understanding, may be very demanding on compute, while eye and hand tracking are very sensitive to latency and are used much more frequently. This brings us a very interesting research problem, which is how do we enable all of those different applications that show very different requirements on a single piece of hardware. So here is a summary of challenges we face to enable on-device AI in AR devices like glasses. So this is a quick takeaway of what we've talked about so far. From the application side, we need to support heterogeneous applications, which can stress the hardware in many different directions. Also, we need to provide the experience that there will be no user perceivable latency. Last but not least, we need to be able to process very high resolution data, which is very critical to a good AR experience. However, from the system side, we are also extremely constrained. We are looking at delivering the efficiency that is 1 to 2 orders of magnitude better than where we are right now. We also need to deal with a limited amount of resources like compute, storage, and memory bandwidth. Now, for most of the time, if we need to process high resolution data at very low latency, we will expect to have relatively beefy hardware. Or if we have very constrained systems, we will only do very simple tasks or only process very lightweight data. But to enable a good AR experience, we really need to achieve both at the same time. So the question is, how do we do that? In the rest of the talk, I'll give you one example and walk you through some of the research we're doing to enable it. So specifically, let's take video understanding as an example. Video understanding is an AR experience that helps you to understand the user activity and environment. It takes continuous frames, oftentimes at a very high resolution, as the inputs and try to reason from it. At the course level, you will try to understand the user's environment, such as if you're surfing, playing basketball, and many other different activities. At the finer grain level, it also digs into localized details in the frames, such as activity of different people and objects as shown in the figure on the right. Based on this information, video understanding pipeline can help provide personalized, proactive, and context-aware assistance for the user. So say you're out with your dog and you say to your AR glasses, take pictures of my dog playing with ball. You not only want the AR device to recognize the dog, you also want it to recognize your dog instead of other dogs. That's why it has to be personalized and context aware. Even better, the system may recognize something interesting you care about and automatically capture that for you. That's why being proactive also matters. However, enabling on-device video understanding is not trivial. First, we have a very limited amount of labeled video data. Second, a video understanding requires taking continuous frames as input, which can lead to very high system cost for sensing and data transfer. Last but not least, the compute and memory costs of processing high-resolution data are also very high. So to deal with these issues, we have looked into the following directions. On the data side, we study techniques like data augmentation and self-supervised learning. To reduce the system cost for video modality, we propose to leverage different sensor inputs on the AR glasses. Also, to reduce the inference cost due to the high resolution, we focus on hardware-aware model designs. So today, I'll focus on the research we do on the deployment side. Mainly, there are two deployment bottlenecks for video understanding: the camera cost and the ML model inference cost. A typical camera sensor has the power overhead of around tens to hundreds of milliwatts. If we were to run it continuously, it can easily become a huge overhead, and we cannot sustain all-day battery life. Also, not to forget that we are capturing high-resolution data, and the data transmission cost itself between the sensor and the SoC can also become very substantial. On the model inference side, typical models for video processing are very expensive. It can easily take hundreds of gigaflops in order to understand the environment and the actions around the user. So how do we go around those different bottlenecks? One of the ideas we have is to take a cascaded approach. Basically, we use cheaper sensor modalities as the trigger, such as audio data from the microphones and motion data from the IMU sensors. And when something interesting happens, we can then initiate the camera to capture and reason about what's happening around the user. And because capturing and processing audio data is usually orders of magnitude cheaper than images, on average, we can reduce the amount of processing by several orders of magnitude. Not to mention that we are saving on the camera sensing and data transmission cost for the majority of time. So let me give you an example. When you are walking around town and you choose to enable the video understanding functionality, for most of the time, only the microphone will be on, and it will detect the transitions in the environment and actions that's happening around you. The data at this stage is quite small, maybe in tens of kilobytes, and the model is also quite small, only in tens of megaflops. If the model detects something interesting might be happening, it can turn on the camera to capture a few frames. Now the input data becomes much larger, in hundreds of kilobytes, and the data is also a bit larger. But it can understand more precisely what's happening. In this case, for example, maybe there's a basketball game. And if this is something that the device thinks you'll be interested in based on your preference, it can go into full action where it starts taking continuous frames and combine that with the audio inputs. This is when we are going further and doing multimodal AI to further improve the accuracy. The inputs get very large here in tens of megabytes, and model is much, much larger as well. But now it can detect much more fine-grained actions and maybe capture the interesting moments for you. This is an example of how we can use a cascaded approach to achieve the balance between system energy efficiency and usefulness of the applications. So far, we've talked about solutions at the algorithm front. Now let's switch gear to the hardware front. Here, I'm showing a cartoon picture of what a typical SoC looks like. We can have many different components, such as an application processor and different IPs for things like speech and vision processing. Nowadays, it's also very common to have ML accelerators in the mix. All of those components will sit on a system bus for communications. So this is a typical way to do it. But a better way, from our perspective, is on the right-hand side, in which case we'll have dedicated ML accelerators being distributed into individual IPs. First, because of the heterogeneous nature of the different applications, we can have ML accelerators for each of them to be tuned to the needs of different applications, instead of just using one very beefy accelerator, which will sacrifice efficiency for each of the application. Second, it also saves a lot of energy on the system bus data transmission. By distributing ML acceleration, it keeps data local, reduce contention for bandwidth on the system bus, and overall can achieve a much better overall system efficiency. So now we've talked about using cascading approach on the algorithm front and doing distributed processing on the hardware front. Where this naturally leads to is toward near sensor compute. Similar to the cascading approach, we can offload some of the processing from the SoC to the near sensor compute. This has two benefits. First, it works just like other cheaper sensor modalities. We only turn on the main processing units in the SoC when something interesting happens. This is beneficial because sometimes using audio or motion signals may still not be accurate enough. Second, when we turn on the SoC, we may not need to send the raw data to it. Instead, we might be able to only send the preprocessed features or even the inference results, which could be much, much smaller. And this can further simplify the system design to use a cheaper physical link between the sensor and the SoC. Next, because we have the processing very close to the sensor, it also opens up the possibility for sparse processing and sensing. For example, we can use the near sensor processing results to skip capturing a few subsequent frames, or even just capture a subregion in future frames where we think the object of interest locates. So you're saving a lot on the actual sensing cost. However, this approach also comes with its own challenges. First of all, the form factor of sensor is a very critical variable to the design of AR glasses, which means that we usually will have a much tighter area constraints for logic at the near sensor side. Also, unlike the SoC, which is usually built on the most advanced process nodes, sensors might be a few nodes behind, which means that the efficiency of the processing might be compromised. This means that going to a near sensor compute setup might reduce the performance or energy efficiency for the overall system. So this is a previous study from Facebook, and it shows that it really takes a certain combination of algorithms, system design, and technology nodes to make the switch to near sensor compute worthwhile in an AR system. Basically, if the compute is too heavy compared to the data transmission cost, or if the technology node of the sensor is too much behind the SoC, then the total energy consumption of the system might be even higher in the near sensor compute setup. So to summarize, there are two key enablers for sensor compute. First, we need to enable cascaded ML models to leverage the multi-stage and distributed compute. This means even for the same modality like vision itself, we need to think about how to divide the task into multiple stages. Second, as compute intensity is really a key here, we would like to design a model that could take the full advantage of the hardware we have, which means doing hardware-aware network design is extremely important. So to optimize a model for a particular hardware, neural architecture search has been a widely studied. Unfortunately, I don't have time to talk about the specific innovations we've been doing in this area, but this figure gives you a high-level idea of the approach we're taking to use NAS for software and hardware co-design. Basically, we use NAS to feed a hardware profiler, which can provide a direct feedback on how the model performs on our hardware. This can include things like latency, energy consumption, memory bandwidth requirements, and more. The information is then used to further guide the search process of NAS along with the accuracy results. Together, this loop continues until you get the results you want. So for example, as you can see on the right, we can use this approach to either keep the same hardware processing latency, but improve the accuracy of the model, or keep the accuracy the same, but instead improve the processing latency of the model a lot more. And we have been using this approach for almost all of the models we're building at Facebook. And this brings me to my last slides. I talk about the challenge we face in AR and the hardware software co-design we're doing to improve efficiency. But there are still a lot of different future directions that could be interesting for research. One is using the ML framework to achieve the network and hardware co-optimization. Right now, we are using a more iterative approach between updating the hardware and algorithm. But if that's possible, maybe we can put the design parameter of both sides in a single loss function so we can optimize them together. The second is lifelong learning. We say that the models really need to run the class in a highly personalized manner. They need to understand the nuance of each user because each of them are different. So having the capability to do some learning on device can be very important. This is also an important area that we expect to see interesting works in the future. And with that, this is the end of my talk. I think this is a very exciting area for research, and we still have a long way to go. But I'm looking forward to working with all of you in the community to bring it into a reality. Thank you very much, and I'm happy to take questions.
Thank you very much. We're a little short of time for questions, but I think we should nonetheless do so. Firstly, let me emphasize that if you have a question, please, you're invited to type your question into the YouTube live chat, and I hope you'll do so. There's some not yet any questions, but my job as your chair is to try and provoke some of those questions. We have a number of people around the panel today in the Zoom call who might also have questions. But while you think of them, let me ask you a little bit about some of the kind of fundamentals here. So you talk about the energy cost of running a camera, and if we have an always on camera, we've already trashed our battery for the day. Obviously, we might think about activating a camera occasionally. We might think about having a low power camera and a high power camera that you turn on when you need it. How much of the energy cost of a camera is to do with the sensing itself, and how much is to do with moving the data off the camera when you found something of interest?
Yeah, so this is a very good question, and we've been studying it. Also, it's a question related to the specific sensor design. In certain applications, we're seeing maybe the data transmission cost can be much higher than the sensing cost itself. But in other scenarios, we're seeing they may be half and half. So I think having some compute near the sensor give us the opportunity to reduce a lot of those data transmission costs. But what we're really looking at is also to enable some sparse sensing. So you use the compute to determine how much actual sensing you need to do a sparse sensing. That way, you cut down both the sensing side of the energy and the transmission side of the energy as well.
Thank you. Well, Terry, I wonder if you'd like to just speak up and tell us your question that's in the chat.
Yeah, sure. So a very interesting talk, Jushin. Thank you. So I guess my question is more about you can potentially have multiple models that you want to be working on processing your input signals. How do you balance this? How do you balance efficient implementation versus general hardware that can cope with multiple models? especially when you're bringing a NAS search into the mix?
Yeah, so there are many different applications that can happen at the same time on the glasses. So we have a mix of first-party applications that we definitely want to optimize for, and we're taking a more heterogeneous approach. So for a few of those really key applications that we expected to run very, very frequently, they might have their dedicated hardware, and we might even use NAS to just tune for the specific characteristics of the model. Of course, we have to reserve some flexibility for some future models, but we will have to prioritize the quality of different applications like eye tracking, hand tracking. Those are definitely the very, very important applications that we need to deal with very well.
Okay.
Thank you. I think we need to keep to time. However, please, there will be a discussion session at the end of this session, and I hope we'll follow up with more questions for you, Hsin, and around these general topics. Thank you in a virtual round of applause for a fantastic presentation.